Hello, we are Krishna, Murali, and Elena Ponce, and we will be presenting our work, Flight Validation of a Global Singularity-Free Aerodynamic Model for Flight Control of a Tail-Sitter. In it, we investigate challenges in modeling and actively stabilizing a particular class of hybrid air vehicle, namely dual-engine, tail-sitting, flying-wing aircraft through an ISAE-SUPAERO made design called Mavion. Tail-sitters, also known as vertical takeoff and landing UAVs, combine the capabilities and long endurance of fixed-wing platforms with the advantages of rotary-wing aircraft, allowing for a single vehicle to exploit a wider flight envelope and achieve energetically efficient high-speed cruise flight while still retaining hovering flight capabilities. Actuator-wise, the Mavion has two motors and two ailerons for airframe control and performing transition from tail-sitting hover flight to cruise forward flight. The flight transition involves significant changes in the Mavion's angle of attack alpha. The Mavion also encounters unusual 180-degree relative airflow velocity during hover, which is not commonly modeled in traditional flight mechanics models. Furthermore, in hovering mode, the direction of airflow, that is, the inexistent airflow in wing sections out of the propeller slipstream, is ill-defined. This situation produces singularities in Buckingham Pi-based traditional flight mechanics aerodynamics modeling, which is based on angle of attack and side-slip angle modeling, angles that become zero in transition and hovering, and make global modeling and control very challenging. To solve these issues, we have previously developed an aerodynamics framework called Phi-theory at our lab, which bypasses the use of these angles and instead is based on 9 scalar aerodynamic coefficients. Additionally, Phi-theory is optimization-friendly since it naturally imposes a global polynomial form on the differential equations of motion, which allows for agile sum of squares-based controllers. Previous work proposed an efficient trim point solver called Phi-trim, which addressed the full longitudinal envelope of the Mavion, especially relevant in transition, ensuring the existence of a unique pair of state x and input u that satisfies the trimming condition, x dot equals 0, for each achievable airspeed under Phi-theory modeling assumptions. Banking turn, or lateral trim points, pose greater complexity. For instance, Phi-trim is not extendable to computer trim points during turns, and our group is still researching for fast and reliable trimming algorithms. Nevertheless, we propose to use traditional nonlinear numerical solvers with initial guesses initialized by Phi-trim. We define a banking turn limit cycle as a periodic solution actuated by a constant input, where each limit cycle is associated with a unique input u and hence identified by its associated v and omega. This yields an attitude description periodic in yaw, but constant in pitch and roll, thus extending the limit cycle description to v, omega, u, theta, and phi. The set of all limit cycle descriptions for a given omega and v is numerically computed for the Mavion using the fsolve routine in MATLAB.
The points v, omega outside the illustrated flight envelope fail to converge to a solution within our acceptable tolerance or maximum iterations. We place no limits on actuation, yet we observed that actuator values are well within reasonable values. Therefore, we concluded that flight envelope limitation is of banking aerodynamics nature, and longitudinal maneuvers such as hover to cruise transition fall within the banking trim envelope. The trimmed flight doghouse plots, also known as energy maneuverability diagrams of conventional aircraft, illustrate their performance during combined turn-climb maneuvers. The left-hand side limit, as you can see, restricts them from flying below a certain relative velocity, beyond which they will stall. This is catastrophic for the aircraft and can lead to loss of control. The Phi trim curves, on the other hand, indicate maneuverability and sustained trimmed flight for the Mavion, even at zero relative velocity, hence precluding stall in tail-sitter flight. The low-speed post-stall conditions modeled by Phi-theory are seen in the doghouse plots for the Mavion. Our Phi-trim results also allow us to define a proposed intuitive pilot interface, unambiguously defined by desired velocities v and omega rather than orientation. This abstracts the internal workings of the drone, relieves piloting efforts, and facilitates straightforward automatic guidance laws. For in-flight control, this work exploits a previously designed gain-scheduled LQR or linear quadratic regulator, which has been validated in simulation. The number and location in the Phi-trim flight envelope of the scheduled points is determined through a regions of attraction analysis. The necessity for gain scheduling is highlighted through simulation results, which demonstrate the instability of a single LQR controller during flight transitions. While hover stability is maintained, transition flight above 10 meters per second becomes unstable due to inadequately tuned controller gains. The velocity v in simulation is slowly incremented by 1 meter per second to prove stability in several points in the middle of transition. In contrast, scheduled LQR controllers ensure stability across all velocities, maintaining system time constants invariant. Flight tests corroborate simulation findings, showcasing successful transition flights and the elimination of instability issues with scheduled LQR controllers. In conclusion, a graphical illustration of Phi-theory derived trim points is presented in the form of doghouse plots, allowing us to conclude that flight envelope restrictions are determined by banking aerodynamics, and previously computed longitudinal trims fall within these envelopes. The expansion of doghouse plots to low speed conditions, even zero hover speed, is now possible to model thanks to Phi-theory. The banking turn trim points are used in the regions of attraction analysis for scheduled LQR design, which is validated in both simulation and experimental flight. Finally, future work will focus on exploiting the polynomial-like nature of the equations yielded by Phi-theory and implementing sum of squares optimization-based controllers for more agile maneuvers. Thank you.